morning students. Today in my physics class I will discuss about the topic field due to a uniformly charged thin spherical shell. That means we have to find out the strength of electric field due to this charged spherical shell, thin shell. By spherical shell we mean that the sphere, hollow sphere. Okay, so due to this spherical charge shell, we have to find out the strength of field in different places. Okay, so in this case, we will have three situations: field outside the spherical shell, field on the spherical shell, and field inside the spherical shell. So one by one, we will discuss and find out, and we will see what is the value of electric field. On what are the factors it depends, the value of electric field. Okay, so for that we have assumed that this is a spherical shell with radius r, center O, and the amount of charge total which is uniformly distributed throughout the entire surface of the shell. Okay. So for this, I can presume that you have learned Gauss's theorem, which I shall use here. And Gauss's theorem, most of you have learned in last chapters that the total electric flux around any closed surface is equal to the 1 by epsilon naught times the charge enclosed. Okay, if a closed surface, say for example, if a closed surface encloses some charge Q, then the electric flux means the number of lines of force passing normally through an area is the electric flux. So the amount of the total electric flux linked to this closed surface, according to Gauss's theorem, is total electric flux divided by phi is 1 by epsilon naught times the say Q, 1 by epsilon naught, where epsilon naught is the absolute permittivity of the free space. So this formula, this theorem, I shall use here to find out the electric field due to this charge, spherical shell. So let us begin with, as I said, there are three cases. So here, to find out the electric field, we will consider a point, and at that point we will find out the, say this point is observation point. Say this is P is the observation point from at a distance R from the center. So P is the observation point. Now in three cases we will see where the P resides. If it is outside the spherical shell, the value will be different. If it is on the spherical shell of radius r, the value will be different. And we will see what will be the value of electric field inside the spherical shell. Number one, when the observation point, when the point P lies outside the shell. So here we will draw a Gaussian surface. As you know what is Gaussian surface? Gaussian surface is a closed surface around any charge distribution where the electric field due to this charge distribution is equal on the surface. So here in this particular case, the Gaussian surface will be a sphere. This is the Gaussian surface. Okay. So if you consider any point on this surface, on this Gaussian surface, the value of electric field will be same. So here P is a point, and this is the Gaussian surface of radius small r. This is already we have considered. And to find out the electric field at this point, let us consider a small surface element. Rather, I will say surface element. Say surface element is ds. and the electric field due to this charge distribution is E at this point P. Obviously, the direction of electric field is a vector quantity. So the direction of electric field is away from the center and radially outward. So here the electric flux, by definition of electric flux, d phi. Since the surface element is very small, so the electric flux linked to the surface also will be very small. So let us consider this is to be d phi. The d phi is equal to, by definition of electric flux, E dot ds, where ds is the area vector of this small surface element. Now see, it is by definition, as you know, the electric flux is defined as the number of lines of force passing normally through an area. So here the area of the ds element is, we have considered to be ds, this is the area vector. As you know, area also can be regarded as a vector whose magnitude is the area of the surface and it is directed outward. So here in this particular case, this surface is like this. So this surface, this area vector of this surface is also radially outward, and electric field vector also radially outward. That is, both of them are along the same direction. So here we can write it to be E ds cos dot product cos 0, because both are in the same direction. So it is E ds. Now the electric flux linked to the entire surface. If you want to find out the electric flux linked to the entire surface, simply what you will do, you will integrate. Here, integrate. Since the surface is closed, so here it is closed integral. Okay, here. Okay. So phi is equal to EDS closed integral. Say here, say, as I said, E is same at all points of the surface. So E is constant throughout the surface. So E will come out of the integration. So it is ds. This symbol is for the closed nature of the surface. Surface is closed. That's a closed integral. So ds. Now if you integrate the surface area of the entire surface, that is the total surface area of the sphere, and that is 4 pi r square. E into 4 pi r square. Okay, so we will find phi to be E 4 pi r square. Okay, so this, remember this result. Now from Gauss's theorem, what we have got, according to Gauss's theorem, phi is equal to Q by epsilon, where Q is the total charge and this surface encloses this total amount of charge. First, so this Q by, so this phi and this phi are same. So what we will write, if you compare this to 1 and this is 2 and this is 1. If you compare these two, then you will find E into 4 pi r square Q by epsilon. So E is equal to 1 by 4 pi epsilon naught Q by r. So this is the result. This is the value of electric field, the strength of electric field at a point outside the charged spherical shell and due to this shell. So 1 by 4 pi epsilon naught, but this, do you recollect this kind of formula have you got earlier? This is the similar to the expression of electric field due to a point charge. Okay, 1 by 4 pi epsilon naught Q by r square. But the difference is that in this case, this is spherical shell. So the spherical charged shell behaves as if the entire charge is concentrated at the center. So this expression tells us about this information. So this is the value of electric field at a point P outside the left spherical shell, E equal to 1 by 4 pi epsilon T by R square, where R is the distance of the observation point from the center of the spherical shell. Or in another way you can say R is the radius of the Gaussian surface. Okay, so this is the first case what we have. Now the second case. In the second case, what will happen? If the point P lies on the shell, now what will happen? In this case, R will become R, because this point we have to consider here. So this R and R will be same. So R will become R. So simply you will put the value equal to 1 by 4 pi epsilon naught Q by R. Q by R. Okay. So this is the value of electric field on the charged spherical shell. Instead of smaller, we have to replace by capital. Okay, 1 by 4 pi epsilon Q by R. So this is the value of electric field on the charged spherical shell. Now the third case. What we have read? When the point P lies inside the shell. So in that case, we have to consider the observation point inside the shell. So we can consider any radius. So in that case, when that is R is less than R. Earlier it was R is greater than capital R, and next R is equal to R, and now this is the case, R is less than capital R. So here, if you consider the Gaussian surface, inside if you consider a sphere, this sphere will not enclose any charge, because the charge resides outside the spherical, outside this Gaussian surface. If you assume it to be the Gaussian surface, then this charge spherical shell, or all the charges lies outside the spherical Gaussian surface. So the Gaussian surface does not enclose any charge. So our expression will become 1 by 4 pi epsilon naught. Q is, it does not enclose any charge, so Q is 0. So it is 0. So inside the charged spherical shell, the value of electric field is 0, because it does not enclose any charge. From this concept, we can get the concept of electrostatic shielding. Electrostatic shielding is the shielding of any object from electric field. So this is here. The field due to a uniformly charged thin spherical shell. We have three cases. One is outside the spherical shell. That its value is 1 by 4 epsilon Q by R square small r. This is similar to the value of electric field due to point charge, and electric field on the charged spherical shell. Its value will be 1 by 4 epsilon Q by R square, capital R square. This is the radius of the charged spherical shell, and inside this charged spherical shell, the value is 0. So this is all about the topic. Thank you very much.